Hello and welcome to this new short video presenting the most recent features of HybriDFEM, a structural analysis method in which a discrete formulation is used in combination with finite elements. Let's start by recalling the main components of a HybriDFEM model. When modeling a wall, for instance, it is first divided into a series of rigid blocks. Those blocks are undeformable, so all the deformability of the wall is concentrated at the interfaces between the blocks, which are called contact faces. Those contact faces are in turn discretized into contact pairs, which consist of two bidirectional springs in series. Nonlinear material behavior or nonlinear contact laws can be used in HybriDFEM by assigning the appropriate constitutive laws to the springs. One of the main strengths of the method is the possibility to couple it with finite elements in a single numerical mockup. In this example, pushover analysis is performed on a two-story building which includes a masonry wall at its upper story. The out-of-plane response of this wall can be complex to capture, as it involves rocking of blocks, cracks opening or closing, and complex boundary conditions. Modeling the whole building only with discrete elements would result in a high computational demand and an unnecessary level of detail in a large part of the structure. With HybriDFEM, we can model the masonry wall with discrete blocks while modeling the rest of the building with finite elements to account for its deformability. By doing so, we can capture complex out-of-plane behavior, such as this crack traveling downwards in the masonry wall as the applied force increases. Recently, the HybriDFEM method was extended from members discretized only along their longitudinal axis to bi-axially-discretized members, which has significantly broadened its scope of application. Among others, this extension allowed to capture complex phenomena such as St. Venant's effect in a beam, showing how the stresses propagate inside the member, or to compute the in-plane response of masonry walls. The extension to biaxially discretized members led to the necessity to develop a contact detection algorithm which would automatically detect the interfaces between blocks. The one developed for HybriDFEM is based on a preliminary detection of potential contacting blocks by checking if the smallest enclosing circles of two blocks intersect. If they do, the second step of the algorithm consists in checking whether the two blocks share a common vertex, detecting the zone where the two vertices overlap. Several new extensions are on their way, such as the extension of HybriDFEM to modal analysis, modeling the steel-concrete bond in reinforced concrete, or performing full nonlinear time historic analyses, taking advantage of the coupling to drastically reduce the computational demand. Publications presenting those extensions will follow. If you want to know more, the newest features of the HybriDFEM method are presented in this paper, recently published in the journal Structures. Other benchmark examples and publications relative to HybriDFEM can be found via this link. Please do not hesitate to reach out to us. We will gladly discuss HybriDFEM with you or provide more information.